We were just looking at area under the curve. We were given the graph and the shaded region, and we had to find that area. So now let's say that we're not given that graph and we're trying to find that area. So let's go through this. We talked about this again earlier this week in class, but in summary, to find the area bounded by f of x and x equals a and x equals b and the x-axis, use the following steps. So it's helpful if you could first sketch your graph. And I was thinking last night, oh, well, maybe they wouldn't know how to sketch that graph. And then I was thinking, what the heck? They're in calculus. We've been learning how to sketch graphs. Yes, they could know how to sketch that graph. So that could be actually a cool kind of problem later on for a test. But anyway, so you're going to sketch the graph, and then we're going to find any x-intercepts of f of x on that interval that we're looking at finding the area. Then divide the region into subregions, depending on if it's above or below the x-axis. The definite integral will be positive for the subregions above the x-axis, and we've talked about it would be negative for the subregions below the x-axis. So we're going to use separate integrals to find the positive areas of the subregions. And so basically we're going to take the absolute value of the pieces that are below the x-axis, and then we're going to total the area, the sum. The total area is the sum of the areas of all the subregions. Okay, so I have an example there before us. The example says f of x is equal to 9 minus x squared. And we want to find the area bounded between the x-axis and the curve on 0, 6. So there's different ways to approach how to graph this. We can use algebra. This I could tell is a quadratic, so I know it's a parabola. It's also in the fact that it's written that I can use transformations of graphs. Excuse me. I could rewrite this as f of x is equal to, maybe you'll see it better like this, negative x squared plus 9. So I know this minus sign, that makes it so that my parabola is reflected across the x-axis. So something that was normally like this, just x squared, negative x squared is reflected across the x-axis. And then this plus 9, this shifts the graph up 9 units. And so I have this graph here, up 9 units. So looks something like this. So how would you do that? I know this is not going directly into the question, but how would have we done that if we were using calculus to sketch that? Well, you would need to know where it was increasing, decreasing, where it had a max. We could find concavity. Okay, I'm not going to go through that because that's not that part right now, and we're running low on time, so I just want to get through this example and a couple of other ones. So let's continue on. We have to find where this is crossing the x-axis. And we know that we want the bounds between 0 and 6. So one of my bounds is on this side. 0. So let's figure out our x-intercepts. And our x-intercepts occur when y is 0. So we're looking at 0 is equal to 9 minus x squared. So there's a couple ways that we can solve that. We can factor it and set each factor equal to 0. Or I notice I could add x squared to both sides. X squared equals 9. Take the square root, use the square root method. So x is equal to plus or minus the square root of 9, which is 3. So I have two separate x-intercepts. We have one here at -3, and we have one here at +3. But we want the interval between 0 and 6. And so we're looking at this graph. And so we're looking at the area. You get the idea that it's for some reasons not drawn to scale. But we're looking at this area in here bounded. And we're looking at this area in here bounded. This will eventually hit this line, x equals 6. Okay. So now we know how to split this up as two separate integrals. We're not worried about this -3 because it's outside of our bounds between 0 and 6. And so we have one integral that we're looking at, and that integral is going to be 0 to 3, where it's crossing the x-axis, 9 minus x squared dx, plus the absolute value of the integral from 3 to 6 of 9 minus x squared dx. So now we can go through and we can take the antiderivative. Antiderivative of 9 is 9x minus the antiderivative of x squared, which is x cubed over 3. We're evaluating this from 0 to 3. Plus the absolute value, same antiderivative, 9x minus x cubed over 3. And this is evaluated from 3 to 6. So plugging in our upper bound first for the first integral, plugging in 3 wherever we see an x. If we plug in 3 wherever we see an x, we get 9 times 3 is 27, minus 3 cubed is 27. 27 divided by that 3 is 9, so minus 9. And then we have minus, plugging in 0 wherever we see an x, we get back 0. So that's our first integral. Plus the absolute value. So now we're going to plug in 6 wherever we see an x. So we have 9 times 6, that's 54, minus 6 cubed divided by 3. So 6 cubed is 216, and 216 divided by 3 is 72. So that's just plugging in 6, and then we minus off. Now we're going to go in and we're going to plug in 3 wherever we saw an x. Well, we just saw that over here, right? Plugged in 3, we got 27 minus 9. And that absolute value. So 27 minus 9 is 18, plus the absolute value. So we have 54 minus 72. That gives us negative 18, minus, well, 27 minus 9, that's positive 18, but with a minus in front, so that's minus 18. So we have 18 plus the absolute value of negative 36. So we have 18 plus 36, which gives us back 54 units squared.